Uh, okay. Good morning, everyone. In our last two classes, we covered the fundamental on lexicon analysis and the preliminary steps and the internal architectures of lexicon analyzers. While we have seen that how the finite state machines are implemented inside the lexicon analyzer and the tokens are being generated. Also, in that segment, we have seen that if errors are there, then how the lexicon analyzer find out the errors, which are categorized as a lexical error. But some errors are there which cannot be tracked by lexicon analyzer. Those are named as, those are not named, those may be a syntactical error or semantical error. So those errors are cast in syntax and semantical phase. So today onwards, we'll be focusing on the syntax analysis stage. In this first video, we will be covering the fundamental on syntax analysis, and in the second video, we will try to cover the top-down parts of the syntax analysis. So let's move to that segment one by one. Okay, just a minute. Let me share my screen. Okay. Uh, okay. Now, first, before entering into the specific segment of syntax analysis, like we covered the fundamental part on lexicon analysis, here also some preliminary knowledges are required. The first point that we need to cover, that is called ambiguity. Ambiguity means, let this is a red dot and this is also a red dot. So if I ask you to select a red dot, then you will be confused that which red dot to select, because both have the same color. Or even let I am designing two green dots. So if I am asking you to select a green dot, you will be confused. So here I have a grammar G. I have a grammar G. From that grammar, I have designed a tree that contains two red dot, two green dots. Now I am asking to select a red dot, then you will be confused. If I am asking to select a green dot, you will be confused. Basically, we know for a grammar, there will be definitely a green dot. We change it. This is the rule. This is a green dot and this is a red dot. This is our assumption. For a grammar, definitely we will get a red dot and we will get a green dot. But if that condition, if we deviate from that condition, this type of situation is there, that means a confusing situation is there. In that time, this tree, the second one that I have given here, it is ambiguous tree. Ambiguity means when we are being confused, that scenario is being considered as an ambiguous situation. I hope you can understand the statement. Now, what I have said in the first case, that for a grammar there is a red dot and a green dot. So this point we will be discussing first, that whether a grammar can have a red dot or green dot or not, or whether a grammar can have more than one red dot, more than one green dot or not. So if this architecture is being followed for a grammar, then it is not ambiguous. If this architecture is being followed, then it is ambiguous. Okay. Now, one thing for here, you just remember that this red dot means LMD, leftmost derivation, and right dot means rightmost derivation. LMD means leftmost derivation, RMD means rightmost derivation. Correct? So what is LMD and what is RMD? We will be looking shortly. Okay. Now for example, this is a grammar G. Consider the example number 19 here. So this is a grammar G. It consists of Vn, you know, 4 tuples. This is sigma. This is production rule, and it is a start symbol. Here the start symbol, it is E. That's why directly it is given. So Vn is E, non-terminal. Sigma means these are the terminal values plus asterisk and ID. These are the production rules. Which are the production rule? This one is a production rule, this one and this one. That means E generates E plus E, or E can generate E star E, or E can generate ID. Correct? So if we are not able to understand, I am writing here. E generate E plus E, or another production rule is there. E generate E asterisk E, or even E can generate ID. Correct? Now these are the three production rules given. Here you check that E is being expanded every time. So which is being expanded, that is categorized as a non-terminal. That's why E is coming in the non-terminal part. Which cannot be expanded. So if I eliminate the E segment, all E segment if I eliminate, what is being left? This is plus, star and ID. That means these tokens or these parameters are there which cannot be expanded. That means this will be categorized as a sigma. That's why these are called terminal. Right? I hope already I discussed on the same issue last 2 classes, but still again I have discussed. Now here our point will be, let me erase this segment so that I can write over here. I'm writing the extra part that I have. Sorry, actually I'm erasing the extra part that I have written. Now, you know that for a grammar, last time we have seen, if you can recall, for a grammar, there is a production rule. From that production rule, we realize the language. For that language, we are representing the language in finite state machine. Correct. So finite state machine, it means that for a grammar, there is a production rule. From production rule, we were generalizing in terms of language, and it was accepted by finite state machine. So this machine can be a finite automaton, can be a lower bound automaton, can be a push down automaton, or even it can be a Turing machine. Correct? So because the grammar that I am writing, every time I cannot specify that it will be a finite automaton based structure. It may be a lower automaton based structure basically. Because some production rules are different, then it may be accepted by push down automaton or Turing machine. So this is the architecture, already you know about that. Now for that language, the language that I have taken, now for that language, if some strings are being taken, let a string I am taking S1 string, S2 string like that for this language. You know, in last 2 classes we said that S1 and S2 definitely should be accepted by this finite automaton, because this path is from the grammar to the respective machine to realize that language. Whatever the string that I will infer from this L definitely will be accepted by the machine. Now, if I am taking an arbitrary string, for example, small s9, let this s9 is not being accepted by this machine, which means that this s9 cannot be a part of this language. This s9 cannot be a part of this language. But s1 and s2 if being accepted, then definitely is a part of language, subsequently part of the machine. Okay. Now, in the same way, for example, for this grammar that I have taken here, I have taken a string, like S1 string I have taken. Let the string is ID plus ID star ID. This is the string. Correct. We are not talking about the machine, or we are not talking about the language here. Just we will be focusing on the production rule. That means here our concentration will be on only on grammar and production rule. Correct. We will be the rest of the parts that I have shown here. For conceptual purpose, this is the architecture you need to remember, because every time I will be specifying something that will be correlated with this architecture that I have already defined. Now, if I assume S1 is a string and it is It is a grammar G is being given. So for that grammar, these are the production rules. First, I am clearing one point. These are the parts already being covered in your automata theory paper. These are not new in compiler design. For your understanding purpose, I am covering this section. For this grammar, these are the production rules. Now a string I am taking, this is a string. Now I am predicting that this string is being accepted by this production rule, which it means that means this production rule is generating some grammar. Sorry, not grammar, it should generate some language. I should write. It is generating some language, and I am assuming that S1 is such a language that comes under the L. That means ID plus ID star ID, whatever I have taken, you see the path. From this grammar, the production was there. Let me make it more clear. Let me erase this section so that you can understand it clearly. From this grammar, this is a production rule, right? From this production rule, I have derived a language. For that language, I have taken a string S1. Let the string be ID plus ID star ID. Now, for this string, my objective is how to represent the string using the production rules. I know someone has said that this S1 is a string that belongs to language L. For example, let I am pronouncing a sentence. I am taking the third compiler design class. And this belongs to the category of language L, means English language. Someone has said that whatever the sentence I have said in just a minute before, that comes under the language L, that means it is English language. Someone has said. Now, what we can expect that the English language, which is based on some rules, production rules, and based on some grammar, so my sentence that I have taken, that should be accepted by the grammar and the production rule. The same thing that I have said here, G, P, L, and FSM, the same thing I am repeating over here in a different way. So the sentence that I have pronunciated that belongs to the language L, means the English language, and that English language is governed by some rules and grammars. Correct. Now my objective is how to derive this sentence. I know this is English language L, but how to derive the sentence that I have said I am taking the third compiler design class. Correct. Now see, every time we will be doing something, we need a production rule. Correct. Initially, you may face that these are the complex things. It is not at all a complex things. Once you attain all the lectures one by one, and subsequently you go through the examples one or twice or even thrice, then everything will be clear to you. And these are very interesting parts. You should have a clear knowledge on this aspect. Now, here the production rules are E to E plus E. Here I'm just erasing the upper part so that you can concentrate. Okay, so you can concentrate on the main segment that I have shown here. Forget about the rest of the architecture here that I have given. But you need to remember, whatever the sentences I have pronunciated, the same sentence already I have said in last 2 classes. Today also I am repeating the same sentence. I am not deviating from my earlier sentences. Now these are the production rule. E to E plus E. This is one. Another is E star E. Another is IT. My objective is to formulate this string using these production rules. How I can do it? If I start with E, I am showing first here. From E, I am designing E plus E. Correct? Now let this left E, I am expanding this left E. Or I can expand the right E as well. For example, I am expanding the right E here. E to E star E is possible because it is there. Now, right one I have expanded. The right variable I have expanded. I have not expanded the left variable. Now, in this production, I am expanding the right variable. E generates ID, correct? Then this variable I'm expanding in a different level. So it has a different level, it has a different level. And now finally I'm expanding this ID. You know what is the infix operation or in order traversal? If I drop the node perpendicularly, ID plus ID star ID. So our intention was to get ID plus ID star ID. So this is the tree that I have obtained from this production rule. This is called a syntax tree. Syntax tree is based on the syntax rules. That means this is a syntax. Now, when I am expanding the right variable of a tree, whatever the tree I will be obtaining, that is called RMD tree, rightmost derivation based tree. Because every time I am expanding the rightmost variable, this E first, then this E. After doing so, I am moving to here. After doing the right, the next is this. So this is called rightmost derivation. In the same way, I can make a leftmost derivation as well. That means you have understood that ID, here this was a plus, again this was ID, here this was star, and here was ID. This was a string. Had I started with this, I am writing in a different ink. Had I started with E2, here I don't know whether I will be able to show here or not. This I'm okay. I'm showing. Here I'm showing in a small E2 E start E. This is the production over which I'm starting. Correct. My intention is to generate ID plus ID star ID. So plus should appear in the left part. I am expanding the left variable. E2 E plus E. Correct. Now this E is expanded to ID. This E then expanded to ID, and then finally this E expanded to ID. So again you check, this is ID plus, this is ID, this is star, then ID. The same string that I have obtained here can be derived by expanding the left variable as well. Every time left. For this production, this was the left. For this entire production, this was the left. For this entire production, this was the left. So this one is coming. As this one is being expanded, so next left was this E that is being expanded. Once this E is expanded, the next left was this capital E, so this is being expanded. So this is a tree and this is a tree. So this is called LMD, leftmost derivation based tree. So for a grammar, when some production rules will be given, and if I assume this string S1 belongs to this grammar, means belongs to the language English, whatever I said earlier, then for each grammar, I will be obtaining definitely one more leftmost derivation and one rightmost derivation, exactly one, and exactly, again I'm repeating, exactly one leftmost derivation and exactly one rightmost derivation to obtain any string that belongs to that grammar G. If you take any string, let another string you have taken S2. I am not specifying what is the value of the string. And let someone has said that S2 belongs to the grammar G, then definitely you should be able to get one leftmost derivation based tree, another rightmost derivation based tree. If S2 does not belong to grammar G, then it is not possible to obtain the LMD or RMD. But if S2 belongs to grammar G, then exactly once, at least, again I am repeating, at least exactly once leftmost derivation or rightmost derivation based tree, you can find it out. Now, I am coming to the design here. I was telling this thing initially. For the grammar, definitely you will be obtaining at least one LMD, at least one RMD. If that is the scenario, then the grammar is not ambiguous. But for a specific string, you had taken a string S1. For that string, you have obtained one LMD, one RMD. Now again we have taken another string S1 for that grammar. You have obtained two LMDs, two RMDs, or even it may be a three LMDs, three RMDs. That means more than one LMD, more than one RMD. In that scenario, the grammar cannot be, I cannot tell the grammar is not ambiguous. The grammar is definitely ambiguous. Okay. Let me see the example over here. For example, I am erasing some of the section over here so that you can understand. Now I can explain from the example that I have taken over here. Okay. You see that expansion is this section. Actually, this knowledge is very required before you are entering into the parser part, because every time I need to pronunciate what is ambiguous, what is not, and why the ambiguous grammar cannot be processed through the compiler. These terms again multiple times will come. Now, for this grammar, what we are checking, we have understood what we have understood. We have understood for a grammar, for a string, if I am taking, definitely I will be getting one LMD and one RMD. That is our inferred. That rule we have inferred. Correct. Now, if we are getting more than one LMD, more than one RMD, then the grammar is ambiguous. Okay. Now, my objective, what is here, is to find it out. Let this is a string is given S1. Whether the grammar G is ambiguous or not, that we have to find it out. Initially, we have seen that one LMD and one RMD already exist for the grammar. By already I shown in my previous diagram, by expanding the leftmost derivation and by expanding the rightmost derivation. Correct. Now, here I am first showing how two LMDs can be found from this grammar. I am expanding, E is being expanded. Okay, let me change the color. This is the variable E. E is being expanded to E plus E. Correct. So the left variable I'm expanding first. So let E, this is expanded first. E to ID. It is expanded. Then this E will be expanded. This E is expanded to E study. Then this E is expanded. The left variable is ID, and then the final ID is expanded. Final E is expanded to ID. So again, this is a leftmost derivation based tree, and the expression is ID star ID plus ID star ID. That means the string S1 that we have taken initially. Here we have given the expression by which we have expanded the tree. E generates is the first E plus E, correct? The first expansion that I have taken. Then this first E is represented with ID, and then this E remain left. This is a very well architecture format by which you can generalize it, because every time formation of tree may not be possible, it may take space or time also. So the left part ID is E is expanded to ID. Then this is next left is capital E, which is again expanded to E study. Then what is the variable? Left variable is E. E is represented with ID. Then the right E remain left, and finally this is the ID. The same thing I have represented here. It is projected in form of this production expression. Correct. So every time I'm expanding the left variable. If I had started with E to E study, E to E study, you check E to E study. Then this first left E, I'm expanding to E plus E, left variable. Then for this, what is the left variable? This is E. E is expanded to IT. Remaining is left E to E plus E. That is being left. You can check. Next variable was capital E. So that is being expanded over here IT. This capital E was left. Finally, this is being expanded. So the ID plus ID star ID is the final expression. That means another LMD2 we have obtained here. If we are obtaining two LMDs, that means definitely we will be obtaining two RMDs. If we are obtaining 5 LMDs, then definitely we will be obtaining 5 RMDs. So for this grammar that we have taken here, definitely the grammar is ambiguous grammar because the grammar is generating two LMDs and two RMDs. It may generate more than two or more than three, but we are not focusing on that aspect. Once more than one LMDs are being derived, we can conclude that the grammar is ambiguous. Correct? I hope the idea is clear. Now, one question may stuck into your mind that, sir, how to generate the tree every time, or for which string should I test? That is very important. I said, now, if you had taken a different string which does not belong to the grammar G, then whatever the testing methodology you will follow, definitely it will be incorrect. Your objective should be you need to find out such a string S1 that belongs to the language L, which is connected to this production rule here and connected to G. But if S1 is not belongs to L, then what you can do? Now, here I am showing a shortcut trick here to you that how to identify whether a grammar is ambiguous or not. Actually, these are very important for your examination perspective and as well as your competitive exam and GATE exam perspective, that whether a grammar is ambiguous or not, how you can check it in a very normal way. Correct? Now, here, this is a variable E. It is generating two variables E to E study. Correct? When I'm expanding E, it is generating ID or can generate E to E study. Correct. These are the production. Now, what is our objective? What is the shortcut way to find it out whether a grammar is ambiguous or not? Okay. For that, one more knowledge you require, the concept of left recursion. Okay, let me explain the left recursion first, and then you will be able to understand what is ambiguous. Let E a variable. E is generating E star E. Okay, I am writing in a different way. Every time I am giving example of E, then it's not good. If I am writing A to A alpha and it is in beta, A is a, here I am specifying that A, it belongs to Vn. It is a belongs to symbol. That means it is a non-terminal. And alpha and beta, it can be a belongs to Vn union sigma. So alpha and beta may be a terminal, may be a non-terminal. We are not bothering on that. May be a terminal, may be a non-terminal. If beta is a non-terminal, then there is a problem. And beta should be terminal. Correct, na? Because otherwise you will not be able to end this rule here. Every time it will goes on and goes on. Now, I'm trying to design the tree. A to A alpha. Again I am expanding A. A is generating A alpha. Again, if I am expanding A to A alpha. You check, and finally if I am representing A with beta, let beta is a terminal. I'm expecting that I should tell here that, for example, here I am changing my here alpha and beta belongs to sigma, for example. They are terminal. Here I am assuming. So, because here once I derive the tree, based on that I have decided alpha and beta terminals. Now A generates beta, and rest of the expression I have followed the productions that I have given, A to A alpha or beta. A generates A alpha. Here A generates A alpha, A generates A alpha, and A to beta. So what is the expression? Beta, alpha, alpha, alpha. But entire tree is inclined to left. Correct? And every time I am expanding the left variable. So this is the part, A is calling the left A. This is called the left recursion. If I change the production in this way, that A generates alpha A or beta. So it will looks like A2 alpha and A. Again it will be alpha and A. Again it will be alpha and A. Then A can generate beta. So it will be alpha, alpha, alpha and beta. Correct? The string, if you project it perpendicularly, no? So alpha, alpha, alpha and beta. So alpha, alpha, alpha and beta will be the string. Correct? And the entire structure is inclined to right. This A is calling the right A every time. So this is called the right recursion. Correct? Here the recursion that we have inferred, it is called left recursion. Correct? I hope the idea is clear. If the same variable is appearing in the left part, that is called left recursion. If the same variable is appearing in the right, that is called right recursion. Correct? Now, I'm erasing this segment because too many things we have written here. Now, we started with this question that how to identify whether a grammar is ambiguous or not. Correct? To understand that objective, we discussed on what is called left recursion and right recursion. And yes, the left recursion and right recursion part are very important in terms of the syntax analysis space. Now, if I consider this production E, what is the left recursion? This is the left recursion part, left recursion, and this capital E, it is the right recursion part, left recursion and right recursion. Simultaneously, if I consider another production rule here, or even if I don't consider, that is, I may not consider. If I find it out a single production, the parent production mainly, the start symbol where it originates, if left recursion and right recursion present in a production rule simultaneously, then the grammar will be ambiguous. One way is to check whether the grammar is ambiguous or not by taking a sample string. If two LMDs are being derived or two RMDs being derived, that means more than one, then ambiguous. But every time it is very tough to take a string by which I can derive a tree or by which I can generate two LMDs. So the shortcut technique is, if a production parent production contains two recursions back to back, left and right, then the grammar is ambiguous. If I take one more example, you can check over here. Here I have given what is called left recursion. That part you can follow. Here the left recursion part I have shown here. And also the right recursion part also here I have talked about. Okay, for this grammar, example number 13 if you consider. For this grammar, these are the production rules. Vn, sigma, p and s was there. So Vn actually is s. Sigma means here is a bracket, two bracket symbols are the sigmas. And also epsilon is there, also comes under the sigma. Production rule is this one. And start symbol is s. Vn means s. Again I'm repeating. Sigma means apart from s, what are left? This is open bracket, close bracket, and epsilon. These are sigma. Production rule is two production rule. S generate this one and s generate epsilon. And start symbol is s. Now the question, if someone asks whether this grammar G, which contains this production rule, is ambiguous or not. So one option you have, you can take a string. You have to select a string. Now the question is, which string to select? You need to select a good string by which you can judge. But here I said last time that what was the shortcut method? If it has a left recursion as well as right recursion, this is a left recursion and this is a right recursion. Correct? So this grammar contain left and right both simultaneously, so the grammar is ambiguous. That's why I have shown. In exams, mostly they gives two questions. Either they will give a grammar, production rule. They will ask to prove the grammar is ambiguous, but definitely they will give a string. Whatever the string they will give, they will definitely provide a string. Or in competitive exams, they never provide a string. They ask in 2 marks question that whether a grammar is ambiguous or not. Then directly check whether the left or right recursions are there or not. Correct? Another example again I have given. You should follow the examples very perfectly that I have given. Let this is a grammar, again a grammar, contains Vn, sigma, P and S. Here Vn means the start symbol only S. Sigma means apart from S, what are being left? Small a, b and epsilon, correct? So small a, b and epsilon are the sigma. Production rule is this one and start symbol is S. Correct. Now for this grammar, whether the grammar is ambiguous or not, you can check. So here template string is being given a, b, a, b, a, b. Here I have shown the associated derivation tree LMD1, LMD2, simultaneously RMD1 and RMD2. That means the grammar is ambiguous. You should check the derivation by which I have shown. But again, the same ideology you can apply, that whether this S has a left recursion, this is a left recursion, as well as it has a right recursion. So the grammar is ambiguous. Whether this string is being given to you or not, but you are able to judge the grammar is ambiguous or not by looking at the production rules. I hope the idea is clear. Now, one question may start to into your mind that, sir, why you started the part ambiguous? Because you will be looking shortly when I will be coming into the parser part, that the compiler, in compiler design, if a grammar is ambiguous, then it cannot process that ambiguous grammar. Because already, if you are defining integer a comma a, so do you really expect that this code will run? The same variable you are defined twice, or a that you have defined b and b. I am assuming this is two LMDs. If I am assuming this is two RMDs, though these are not, but trying to map that ideology with this variable declaration. So if someone is asking a equal to a plus b, a equal to s plus 2, then which a to select, this a or this a? Definitely the compiler will get an error. So here the definition that I have provided, that was ambiguous, that is an ambiguous definition. Here also definition is ambiguous definition. So I cannot give an ambiguous definition here. In the same way, the compiler cannot sustain that contain the ambiguous grammar. Correct? This thing you need to remember. I hope that you could understand the example that I have given. Now we are coming to the next point, that is called left recursion. Yes, we have covered the left recursion part, but again we have to cover the left recursion in a different way. Already you know that what is left recursion. If A generates A alpha, okay, first let me write in the production rule format. A generates A alpha or beta. This is called a left recursion because A is appearing in the left part. Correct? Fine. Now, if a grammar contains left recursion, then compiler cannot process that left recursive grammar. Why? There is a reason. Compiler cannot process a left recursive grammar. Now your question will be, then sir, can it process the right recursive grammar? Yes, it can process. You will be asking that what is the proof? What are the proofs are there? The proofs we will be doing. Let me equip you all with some preliminary knowledge. Then we'll be moving into that part. So A2, A alpha or beta, this is the production. I don't know whether alpha or beta is a terminal or non-terminal. In my last example, A2, A alpha or beta, we assumed A is a non-terminal and alpha and beta was terminal. But here we are assuming that alpha and beta may be a terminal, maybe a non-terminal. We are not bothering on that. Okay. Now, if I am designing a string like here, you just check here, A2, A alpha and beta. What are the different string it can generate? Let A2, A alpha. If I put instead of A beta, so it can generate beta alpha. Or if I am starting with A2, A alpha, then if I am expanding this capital A with again A alpha, this alpha will come. And if I am putting A instead of beta, then beta alpha alpha can be a string, or even if I am taking A to A alpha, or even I am taking A to A alpha, A is here. Let me here. I have made a small mistake over here. Should not show this part because it will be repeating the same thing again and again. It is also possible A can generate only beta. Okay, so it will continue. Beta, I should write this in the very beginning because that will be a good one. A can generate beta. So three different scenarios we have seen, or it can be generalized in a different scenario. A is generating beta. It can generate beta alpha, or it can generate beta alpha alpha. It will go on in this format, beta alpha alpha format. So it is generating beta alpha to the power n. So this is the language. Correct? Because every time I am expanding it, A to A alpha, again A to A alpha beta. So you check the progress: beta, beta alpha, beta double alpha, beta triple alpha, beta quad alpha, beta penta alpha, beta hexa alpha. In this way it will goes on and it will be beta alpha to the power n. So this is the language. Now your question is, sir, why you have again coming to the language? You said you will not come. For this purpose, only for this time I will be coming to this language. Later I will never ever will come this language part again. Okay, now if A to A alpha and beta, this is a production is given, then if I am writing in this way, A to beta A dash. Correct. Okay, first before doing so, let me define the grammar here first. G equal to Vn sigma P and S. Correct. This was the four tuples. What was the Vn? Non-terminal. It was only containing A. Sigma means it may be alpha, may be beta, because I don't know whether alpha beta is terminal or non-terminal. Production rule is this one and S is this one. S is means A is the S. Why I am writing, my main concentration will be on Vn part. What I am doing now, here to remove the left recursion part, I am adding one more non-terminal in the Vn part, A and A dash. Initially the grammar was A, the non-terminal part was A, but I am adding a redundant non-terminal A dash in the grammar. Here A is generating beta A dash. Beta means this part I have taken, beta A dash. So the right part, the OR part I have taken, A2 OR part A dash. Then again you should write this A dash to this is A left recursive part. What are left? This is alpha is being left because beta already I have taken. You should write this alpha A dash and only need to write epsilon. What I have done, again I am repeating, A2 A alpha and beta, if there is a production, then A2 beta A dash I should write. Then this A dash is a new non-terminal I have added in the grammar. So this grammar, this A dash should generate the remaining part, that is alpha, A dash and epsilon. Now here only you have to remember this part. Later we will prove that whether this production rule that I have formed is same with this production rule or not. From this production rule, the language is alpha beta alpha to the power n. If from this production rule, anyway I can prove you, I can define beta alpha to the power n, let this is L1 and this is L2. That means both the productions are same. I hope you will be convinced then. Both the productions are same. If both the languages are same, then both the productions are same means both are equivalent. Okay. Again, I am repeating the alpha beta part. Then I will be proving the segment. See, again I am showing A2, if it was there, A2 let A2 A alpha or here beta, then first thing you have to do, you need to write this beta first. A2 beta A dash. So beta part is over. Only thing is being left, it is alpha. So there should be a connection from A dash because A dash is a new non-terminal. A dash to from A dash, what you should generate? Alpha A dash and epsilon. This thing you have to remember. Multiple times this operation you have to perform while designing a parser. That's why 3 times I am repeating the same parameter. A2 beta A dash to alpha A dash or epsilon. Okay. Now I am proving that both the productions are same. Okay. The first proof here. So it was generating beta alpha, alpha, correct? Now A2, I am taking the first instance. A2 beta A dash, correct? Now A dash can generate epsilon. If I am putting epsilon, beta into epsilon, that means beta. The first part, it was beta, A was generating beta, so that is being proved. Now the next is beta alpha. I am starting with A2 beta A dash in the same way. A2 beta A dash. A dash can generate alpha A dash. So let beta A dash can generate alpha A dash. A dash can generate also epsilon. In the next step, beta, alpha and epsilon. What it means? Beta alpha. Epsilon means 1, you can assume. So beta alpha, the second term we have obtained. Third one. A2 beta A dash. Again, I'm starting the same parent production. This is the parent production, first one. Beta A dash. So beta is there. A dash I am expanding here. Alpha A dash. Again, thus A dash can be expanded with alpha A dash. So it is beta, alpha. It is alpha A dash. Now, this beta, alpha, this A dash can be replaced with epsilon. So it is epsilon. So that means it is beta, alpha and alpha. So that means the third one. So we are progressing in the same way. Beta, alpha, alpha. That means we are approaching towards beta alpha to the power n. L1 was the same way, beta alpha to the power n. So both the languages are same. That means the way we have learned here how to remove the left recursion, the productions that we have seen from this production and this production both are equivalent. To prove this both are equivalent, this example I have given. Now the same thing I have given here. You can just see A2 A alpha and beta is there. It should come A2 beta A dash to alpha A dash or epsilon, right? Here some examples I have given. You should see that how I am doing. Example number 16 is there. Let me take a complex example here. E to E plus T, you can assume plus T as A to A alpha and beta, you can remember. E to E alpha, you can assume, and this part you can assume as a beta. Let E is generating E alpha or beta. What is your part? E to beta A dash. What was beta? Beta means T. Sorry, another production is there. No, okay, sorry, this is not another production was there. Okay, perfect. Actually, 3 production this example contains. This is one production. This is another production. This is another production. So after this is a complete production list, and after removal of the production, this is the architecture. Okay. So for the first production, we are removing the left recursion part. You see these 2 segments. For first, E2, E alpha and beta. You know what is the first thing we do? E2 beta A dash. Beta means here T. It is beta. It was beta means T, so beta means T E dash. Then again this E dash will be coming over here. E dash to alpha. Alpha means plus T. So here it is a plus T. E dash. So same way, E to E alpha beta, E to beta E dash, beta E dash, and E dash to alpha E dash. So plus T means it is alpha E dash or epsilon. Correct? In the same way, if you check for the second production, T to T star F here. Here also left recursion is there. Here this part is acting as alpha. This part is acting as a beta. For this, again, this left recursion is being removed over here. Left recursion is being removed over here. Correct? You should check it out here that how this left recursion is being removed from here. Now, here you can check that this ft dash, whatever I am doing here, this is a production that I have removed the left recursive part, and for the second production also I have removed the right recursive part also. So both the problems we have mitigated. But one interesting parameter, some more examples I have given here. Definitely you should follow the examples. Example number 16, example number, though they both are the same, this is 17, it should be 17, and also okay, these two examples are given, you should follow it. Now one interesting parameter you check, that once I remove the left recursion from a grammar, immediately a right recursion being generated. A to beta A dash to alpha A dash. So here no problem with the recursive part, no recursion is there. But here you check the right part a recursion is generated. So that point I have marked here, that here already I have made. Once you remove the left recursion, immediately right recursion being originated. But compiler does not have any problem with the right recursion. Again, your question will be, sir, why? That proof we will be looking once we will enter into the parser part. Correct? What so far we have learned? We have learned only that what is called left recursion. We have assumed that left recursion will create a problem for the parser. That's why we need to remove the left recursion. How we can remove? The strategies we have seen. Okay. Now one more term here I have to introduce, that is called left factoring. Correct? This is very simple thing. So three things we will be covering in this basic lecture. One is ambiguous part, one is left recursion part, another is left factoring part. Here left factoring means, let for a grammar G, Vn, sigma, P and S. So Vn means here S and E are the variables. So if I remove S and E, so what are left? Vn means S and E are the Vn, non-terminal. I, T, E and A, these are belongs to, and also B. These belongs to the terminal, correct? Every time I'm showing what is terminal and what is non-terminal, only to make you understand that grammar production rules are from the grammars, and grammar operates over 4 tuples. Every time I'm trying to match it so that you can remember the architecture of a grammar, and later when it is being required, you can recall all the syntaxes of a grammar. Correct. Now, this is a production rule. S is generating IETS or small I capital ETSES or A, or E can generate B. Now you see this fragment capital IETS or this up to here, both are same. If I am assuming this as a alpha, that means this is alpha ES, correct? So if a grammar contains the same preliminary part, then the parser cannot process that grammar. For example, there is a production, it is containing small a capital B D, or it is containing A capital D, capital D, let capital B. This type of grammar a compiler cannot take that have the same input token. Input token means this is A, this is A. Now, if someone asks me to start with A, I will be confused whether to go ahead with this production with this production. This is a problematic part for a compiler. So compiler tells that remove this ambiguous phenomena and let me know with which production should I go. Only give a single production. Right? So how to make it is a single production? This is very simple thing. That S to IETS and IETS. So this alpha part is common. What we are doing here, we are keeping this alpha part in common. So alpha, correct? And we are adding one more variable S dash, correct? So S dash means for here, S dash means epsilon, means nothing. Here S dash means ES part. I hope it is clear. Here S dash means epsilon, nothing. Here S dash means ES, correct? S also generate A, so that A part also we have written. This S dash that I have written, it may be epsilon, may be ES. So this S dash may be epsilon or may be ES. Only that part I have written. Rest part is remain same, E to B. This is very simple. If the same front part are there in two productions, we need to merge them in a single production such that we can give a exact pathway to compiler from which to originate or from where to start. Okay. So this is called left factoring. If a grammar contains this type of architecture, the grammar needs to be left factored before it is processed by a compiler in the syntax analysis phase. Okay. So if I summarize what basics fundamental part we have covered, one is called ambiguous grammar. Ambiguous grammar means if a grammar has two leftmost derivation or more than one leftmost derivation or more than one rightmost derivation, then the grammar is ambiguous. The shortcut trick was if a grammar contains left recursion as well as right recursion simultaneously, then the grammar is ambiguous. Second part was what is called left recursion and what is called right recursion. How to remove left recursion, that also we have seen. And third part was how to remove the left factoring part in a grammar. So how the grammar can be left factored. Correct? That part we have covered. In our next example, we will be covering some more fundamentals. This is the first fundamental segment. Then we will be moving to the parser.